Understand the concept of successive ionization energies. Ionization energy, i.e., is the energy required to remove an electron from a gaseous atom or ion. Successive ionization energies, IE1, IE2, IE3, etc., represent the energy required to remove electrons one after another from the same atom. Recall the difference between valence and core electrons. Valence electrons reside in the outermost occupied shell and are shielded from the full nuclear charge, making them relatively easy to remove. Core electrons are located in fully filled, inner shells closer to the nucleus. Because they experience a much stronger effective nuclear charge and are closer to the nucleus, removing a core electron requires a massive, disproportionate jump in energy. Analyze the given ionization energy data mathematically. Look at the differences between successive ionization energy values in the table. First, give second. 1,817 minus 578 is equal to 1,239 kilojoules per mole, an increase of about 3.1x. Second gives third. 2,745 minus 1,817 is equal to 928 kilojoules per mole, an increase of about 1.5x. Third gives fourth. 11,577 minus 2,745 is equal to 8,832 kilojoules per mole, an increase of about 4.2x, representing a massive energy jump. Fourth gives fifth. 14,842 minus 11,577 is equal to 3,265 kilojoules per mole, an increase of about 1.3x. Determine the number of valence electrons. Because the colossal jump in ionization energy occurs between the third and fourth ionization energies, the first three electrons are relatively easy to remove, meaning they are valence electrons. The fourth electron is extremely difficult to remove because it is a core electron. Therefore, the unknown element must have exactly 3 valence electrons. Identify the element. Look at the options and find the element with 3 valence electrons. Aluminum, Al, has the ground state electron configuration 1s to the power 2 2s to the power 2 2p to the power 6 3s to the power 2 3p to the power 1, which translates to exactly 3 valence electrons in its outermost shell, n equals 3. Removing the fourth electron from Al requires breaking into the highly stable, lower energy 2p subshell, which accounts for the massive transition from 2,745 kilojoules per mole to 11,577 kilojoules per mole. This identifies option B as the correct choice. The correct answer is option B, Al, because of the large difference between the third and fourth ionization energies.